Hi students, welcome back to the chapter 2 lecture, the chemical basis of life. This is part 2 and we'll cover some of the interactions that occur when atoms interact and some other topics as well. So where we left off last time was learning that the electrons in the valence shells of atoms, 1, represent energy, and 2 are the electrons that are responsible for the behavior of the atom, and 3 responsible for creating chemical bonds or attracting other atoms or creating bonds between other atoms. So we know that bonds are formed when atoms interact, and there are a variety of bonds that can form. Remember, those bonds represent energy. So when a bond is formed, that bond represents energy, and if that bond is broken, energy is released. Remember that the valence shell electrons dictate how many bonds will form, and remember that a valence shell would really like to have 8 electrons in it. That would make it stable. But for instance, if there are only 6 electrons in an atom's valence shell, that atom would really like to add 2 electrons to become stable. So there are 3 main ways or main types of bonds that form. One is called an ionic bond, the other is a covalent bond, and the other is a hydrogen bond. So I'm going to give you examples of those as we go along. So the first one is an ionic bond. And let me just explain to you what an ion is first. I'm not sure if I did that in the first part, but it won't hurt just to have a review. So an ion, there are 2 types of ions. There's what we call a cation and an anion. So a cation has a positive charge, and an anion will have a negative charge. And they don't need to be single atoms, right? They can be whole molecules that act as cations or anions. So remember that atoms become cations or anions, or have a positive charge or a negative charge, depending on whether they've picked up an electron or lost an electron. So cations form when they have a loss of electron, right? Because electrons are negative, so if you lose something negative, you're positive. And anions are formed when they gain an electron. Okay, so that's what ions are. Sodium and chloride often exist as ions, and this is kind of the classic example for ions, is that sodium often exists as a cation with a positive charge. And the reason for that is it's very vulnerable. Look, it's got that 1 electron in its outermost shell, and that's it. Remember, sodium would really like to have 8, but because it has just 1 single electron in its outermost shell, in its valence shell, it's quite vulnerable to having that electron kind of stolen or borrowed from it. So when it comes into contact with another atom that's an anion or has a negative charge, that electron is easily pulled away from sodium. So look at chlorine, for example. It's got 7 electrons in its valence shell, so it's very electronegative. And when these 2 atoms come together, the electron in sodium's valence shell often gets pulled over to calcium. And so since sodium now has lost an electron, it becomes positively charged. It becomes a cation. And then when that electron is stolen, chlorine is pretty happy because it now has 8 electrons in its valence shell. And so that attraction then between those atoms creates this molecule that we call sodium chloride. That's table salt. So written like this, sodium chloride, and that's the stuff you might put on your French fries or I don't know, salt your meat with. So that's an ionic bond. And then next up are covalent bonds. Think of co as meaning sharing or shared. So this is where two atoms share a pair of electrons, where one atom isn't more electronegative than the other. They are mutually sharing that electron. And there are two types of covalent bonds. Non-polar covalent and polar covalent. So I'm going to give you examples of these here real quick, but let me just give you a definition. A non-polar covalent bond is created between atoms that share electrons equally. And polar covalent bonds, the electrons, it's still a covalent bond. They're still sharing the electron, but in a polar covalent bond, one atom pulls on the electron, or the electron is closer to one atom than the other. And this usually occurs when one atom has greater electronegativity. So the electron isn't stolen like in an ionic bond, it's still shared. It doesn't get taken away from the one that's less electronegative. It just means that the electrons in the more electronegative atom have a stronger pull on those electrons. Okay? Polar molecules then end up having a separation of charge. They're not ions. They're definitely not ions because they haven't had electrons added to them or taken away from them. But what we find is that one end of the molecule ends up being slightly negative and the other slightly positive. And let me show you an example of this here in a second, and it'll make a little bit more sense. When you just kind of say it in words like that, it's hard to visualize. Let's look at some examples of covalent bonds. So this, when two atoms of hydrogen come together, they are going to equally share those two electrons. So this example is a non-polar covalent bond. Hydrogen has one electron. Its atomic number is 1. And remember how electrons are distributed around the nucleus. Here's the nucleus. It would have one proton and one neutron on the inside of there. And for hydrogen, hydrogen just has one lonely little electron in its outermost shell, its valence shell. And that first shell can only hold 2. So what hydrogen really wants to do is pick up another electron to be stable. And so hydrogen often bonds with another hydrogen atom in a non-polar covalent bond. So let's say this electron belongs to that hydrogen, this electron belongs to this hydrogen. They are both sharing those electrons equally, so that makes it a non-polar covalent bond. And the same is true with molecular oxygen. This is a non-polar covalent bond, but there's a double bond there. So remember that oxygen has 6 electrons in its outermost shell. Let's count them. 1, 2, 3, 4, 5, 6. Oxygen would really like to have 8 in that valence shell. So it easily creates a non-polar covalent bond with the with another oxygen, because each one of those oxygen atoms is really looking to pick up 2 electrons. So remember, a double bond is created when atoms share 2 electrons, and that's exactly kind of what's happening here with oxygen. Let me draw those bonds in just so you can see. There's a bond created between those 2 electrons, bond created between those 2 electrons. So that's a non-polar double covalent bond, but still a non-polar covalent bond. When we look at a water molecule, though, for instance, this is a great example of polar covalent bonds. This oxygen atom in the center has 1, 2, 3, 4, 5, 6 electrons in its outer shell, its valence shell. So it's really electronegative. And so it's going to attract the electrons from hydrogen. And so it's going to have a really strong pull on those electrons in hydrogen, and it's going to have the ability to hold those electrons closer to the oxygen than the hydrogen. Let me show you of this. Okay, I know this is a little blurry, but remember that oxygen is very electronegative. So that means it has a lot of electrons in its valence shell. And so when it pulls on, let me use a different color, when it kind of yanks on that hydrogen's electron, that hydrogen's electron gets pulled closer towards the oxygen atom. And when you have an electron that's closer to one atom than the other, you're kind of gaining something negative. So this end of the water molecule has a slight negative charge, but since hydrogen hasn't lost its electron, but the electron is further away from the nucleus of the hydrogen, what happens is the hydrogen side becomes slightly positive. So now we've got a molecule that has a slight negative charge on one side, slight positive charge on the other. This is not an ion because the electrons haven't been stolen. They're still being shared. It just means that the overall molecule has a slight negative charge on one side, slight positive charge on the other. Okay? Here's another way to look at this. I've lost a little bit of formatting here, but this side of the oxygen, or side of the water molecule, is going to be slightly negative. The hydrogen side is going to be slightly positive. And so this creates a molecule, water, that has an overall net charge of 0. It's not an ion because we haven't completely taken electrons away or added them in. It just means overall slight negative charge on one side, slight positive charge on the other side. And this gives water some really unique properties that we're going to talk about here in a few minutes. And then the third type of bond is called a hydrogen bond. And we've just really seen a hydrogen bond when it bonds with oxygen, but let me tell you a little bit more about a hydrogen bond. And a hydrogen bond forms between a hydrogen atom and an electronegative atom. Think of hydrogen atoms as being pretty weak. Remember, they only have one little electron in that valence shell, and whenever they come in contact with or come near a very electronegative atom, they're susceptible to being kind of sucked in or drawn towards that electronegative atom. Hydrogen bonds are a little different in they're not, we like to say that they're not actual chemical bonds, and the reason for that is they don't make atoms into molecules, and they're very weak, so they can very easily be broken. So more so, hydrogen atoms are going to, if you think about a really long molecule, a really large molecule, the areas where you have hydrogen atoms in that molecule tend to stabilize areas where you have slight negative charges. So they're really responsible for creating or stabilizing large molecules. They aren't officially able to make atoms into molecules. They exist, but they're more so involved in kind of holding different parts of a large molecule together. Let me show you here. So here's water, and remember that the hydrogen ends of water are going to be slightly positive, oxygen end is going to be slightly negative. Another example of a molecule with polar covalent bonds, is ammonia, where it's got 3 hydrogen atoms bonded to it, and then the big nitrogen is very electronegative. And so if you were to mix ammonia with water, then hydrogen bonds can very easily form between water and ammonia, but they're very weak, and they aren't going to create molecules. They really just sort of create attractions between molecules. We can see what happens when we put more than one water molecule together. So you see what happens with water is, remember this is hydrogen and that's the oxygen. The positive end of one water molecule is attracted to the negative oxygen end of another. So this is what one of the things that gives water its properties, right? Is that, or allows water molecules to stick together and give us liquid water. If this weren't the case, then we wouldn't have liquid water on our planet. But because of this polar nature of water molecules, they tend to be attracted to one another. And this gives us liquid water on our planet. So let me skip this first slide. Okay, so that brings us to why is water so important? And I mentioned earlier that it gives us, or gives the planet life properties, or water has life-giving properties. Because it's polar, it attracts other water molecules to create liquid water. And another thing that occurs is that it's really resistant to temperature changes. And the reason for that is it requires a lot of energy to break hydrogen bonds. So think about boiling a pot of water. You have to add heat for a significant period of time, and enough heat for that matter, to get the water from liquid to, for instance, a vapor. And what you're seeing when it's boiling, when you see that liquid water boiling and you kind of see the steam coming off, is you're physically seeing the hydrogen bonds being broken, and that liquid water is now disassociating. The hydrogen bonds are breaking, and the water is changing state. So if you were to just leave a pot of boiling water on the stove, eventually you'd come back and the pot would be completely empty. So all those hydrogen bonds would have been broken. The water molecules disassociate or come apart, and they end up just in the atmosphere. So that's one thing. Another example would be how long it takes for water to boil. Or let me give you this example. Let's think about a lake in an area where it's had a cold winter, and now it's spring and getting into summer, and that lake still is quite cold, even though it's been warm for maybe a couple of months, right? And the reason for it taking a long time for that water to warm up is that while the sun is shining on that water, the hydrogen bonds are absorbing that sunlight energy, absorbing, and it's going to take a while for that water to change temperature because the hydrogen bonds are absorbing a lot of energy. And so another good example of this, or why these hydrogen bonds are important for liquid water and giving us life-giving properties is, if you think about it, our planet is about 4 billion years old. And the sun has been shining down on our planet for 4 billion years. So that's a lot of energy that's been shining down on the planet. So why have our oceans and lakes and rivers not completely dried up? Obviously, we get rain, right? But if you think about it, the Pacific Ocean has been there forever. Why is the Pacific Ocean not 150 degrees? It's because there's so much water and it's so deep, and it would require so much sun energy to break all of those hydrogen bonds in order to increase that temperature of the water. So the water on our planet actually helps to maintain the planet's temperature. That water absorbs that sunlight energy so that our planet doesn't get too hot. Another property of water is that it has what we call cohesive and adhesive properties. And I'll show you a cute little picture here in a second that really allows you to see this in just one second. And then also, you probably know this, you probably see this in your house or in your daily lives, that water dissolves other substances, most other substances. It will dissolve other polar substances, other polar molecules, and it will also dissolve ionic substances. So we often call water the universal solvent. What water cannot dissolve is non-polar substances. So things like lipids, fats, oils, right? You need something to help out with dissolving lipids. You can dissolve lipids and other lipids, but water alone doesn't dissolve a lipid. Think of oil and water. If you were to mix it up in a bottle, it looks as though the lipids and the water have come together and mixed completely. But if you let that bottle set a little bit, you'll see those things separate out with the lipids or the fats on top, the oil on top, and the water on the. Okay, so let's look at water's cohesive and adhesive properties. So cohesion is where one water molecule sticks to another water molecule. And we know that's because of their polar nature, right? So cohesion is water molecules sticking to other water molecules. Let me give you an example. Or you could even try this at home. Try it with your kids or little brothers and sisters or even your parents. If you hand wash your dishes and you were to set them on your kitchen counter without a paper towel or not in a drying rack or not on just a towel that would absorb the water. Imagine taking a glass, rinsing it out, and setting it upside down on your kitchen counter without anything on the kitchen counter. And what will happen is that kitchen counter will eventually start to get wet as the water drips off the glasses. And what will happen is the water will start to drip up off of the counter, right? We know that water, if there's enough water on your kitchen counter, it starts to roll down the counter and drip off down to the floor. That's an example of cohesion. You get one water molecule kind of rolling down and it pulls all those other water molecules down with it and creates that nice puddle on the floor. If you do that, if you put that glass on the counter, that moving water, that rolling water, will pull the glass or slide the glass around on the counter as well. As those water molecules start to drip and fall off the counter, the water molecules on the counter are bonded to the water molecules in the cup, so it kind of pulls on that cup. And then lastly, adhesion. This is where this is a property of water where water really likes to stick to other molecules other than other water molecules. And this is really important. Let me go back to this one real quick. This is just showing you, it's a cool picture. It's just showing you water sticking to water, right? So if you had dropped a rock in the water or something drops in the water, you often see that dip in the water first and then the water kind of shooting up. And that's because when you dropped whatever it was in there, you broke some of that surface tension and you broke apart some of those water molecules and created a little wave, and that wave then pushes water up. And because those water molecules want to stick together, you've got this little mountain of water. Go to adhesion. This is really important for plants. Think about our huge sequoias and our redwoods in California. Those huge trees that are hundreds, if not thousands of years old. They're very tall, some upwards of 100, 150 feet tall, where the roots are where the water is, right? How does that water get all the way up to the top of that tree? And the way it does that is the water gets absorbed into the roots and the water sticks to other molecules inside the tree. And so even against gravity, you get water being pulled up the tree into the tallest of the branches. And then eventually water evaporates like they're showing you here, right? So it kind of creates this escalator of water from the roots all the way up to the tops of the trees. So this is one way in which water provides its life-giving properties to living organisms on our planet. Okay, one other example here of water's cohesive properties is that it creates what we call surface tension. And like I said, remember, it takes a lot of energy, not just heat energy, but could be energy like kinetic energy, the energy of motion. it takes a lot of energy to break those hydrogen bonds. So this organism right here is called a water strider, and you see it literally walking on water. And what's cool is you can see the water kind of bending right here. So there's the weight of this insect is putting stress on those hydrogen bonds, but isn't enough to break those hydrogen bonds. So that's how some of these insects get to walk on water, because of those bonds. Okay, so that's liquid water. Let's talk about what happens when water freezes. So, kind of just to step back to a general chemistry course, and this is a topic that we sort of address in either next week's lab or the week after, that all molecules in all things are constantly moving. Even in those things you see as a solid object, maybe it's your chair or your desk or a blanket. All those things are made of molecules, and those molecules are constantly moving around, right? In solid objects, like your desk, those molecules are barely moving around. Obviously, your desk isn't moving around, right? But those molecules still make minor movements, but not as much as, say, molecules in the atmosphere, those things around you. If we think about water, for instance, and the molecules that make up water, remember that they are polar molecules, and they really like to bond. Water has that those cohesive properties, right? Water molecules really like to bond with other water molecules. So in liquid water, they are bonded to one another. They're also bonded to one another in frozen water. But something strange happens with water. Normally when molecules, let's just say in the atmosphere, molecules of gas in the atmosphere, it could be nitrogen, could be carbon dioxide, could be methane in the atmosphere. Let's say the temperature of the atmosphere decreases. What happens when temperature decreases is molecules, they slow down their natural vibrations, their natural movements. And normally in the atmosphere, when temperature heats up, molecules start to move faster. They start bumping into one another like bumper cars bump into each other, and then they get reflected and they move off in another direction, and then run into another molecule and move off in another direction. That's normally how molecules work. And that motion, that natural motion that all molecules have, is called Brownian motion. And like I said, as temperature increases, molecules tend to move faster and collisions occur more frequently. And normally, when temperatures decrease, those molecules slow down and collisions decrease. And now that's true with water to some degree. But what happens with water is that when the temperature of water decreases, those water molecules get further apart. They don't get closer together. When those water molecules slow down, they kind of stay still and kind of reinforce their bonds with one another. If this were like any other I shouldn't say any other, but some other molecules, when the temperature would decrease, the molecules would get closer together because they're not moving as fast, and so like the whole gas gets more dense. Water doesn't do that. Water makes these solid bonds, and it kind of keeps other water molecules at a distance. So water doesn't get more dense when it freezes or gets colder. It gets less dense. So less dense means fewer molecules per unit area. So think of how ice forms on a pond, or ice forms on top of your glass of water that you've put in the freezer. The ice first forms on the top, and then gradually, the longer and colder the water gets, then the ice will form down towards the bottom. But because water, when it freezes, gets less dense, it's less heavy than liquid water, it tends to float on the surface. Think about how this affects living organisms. Organisms that live in lakes and ponds and streams that freeze over in the winter. When these lakes begin to freeze in the winter, there's a thin layer of ice that forms on the top, and that insulates the water underneath, preventing preventing excess heat loss. So this is why most lakes, if they're deep enough, do not completely freeze solid. They do not freeze solid. You get a layer of ice, could be a foot thick, could be 2 feet thick on top, and the rest of the water below that remains liquid, and the animals, the fish and invertebrates that live in that lake or that pond, they're able to survive the winter in that water because the water doesn't freeze solid, and the animals that live there don't freeze solid. So that's one of the other life-giving properties of water, is how it behaves when the temperature drops. Another thing I've mentioned is water is called the universal solvent. It has the ability to dissolve, especially ionic compounds. It can dissolve ionic compounds quite easily. So if we started out with salt, if you add water to salt, for some period of time, you'll see the grains of salt in that water, but eventually the salt completely dissolves. And that's because the negative side of the water molecule really kind of gets in between the sodium and the chlorine. And so that negative side of the water really is attracted to the positive side of sodium. And the positive side of water really is attracted to the negative side of chlorine. So you get what's called dissociation. So water dissociates or pulls apart or separates or wedges itself in between ionic compounds. Okay, here are some key concepts that we've just discussed. I'll let you read that. I won't read those to you, but this is essentially what we've just gone over. Now let's talk about substances that we refer to as acids and bases. In chemistry, I know you've heard this. You probably have heard this in just daily life as well. And it seems as though this doesn't have anything to do with water, but it will in a second. Let me just introduce acids and bases to you first, and then we'll see how water plays a role in that. So there is a scale that we use called the pH scale. That pH scale goes from 0 to 14. In the center is 7. Center is considered, or 7, is considered neutral. A solution is considered acidic if its pH is less than 7. And a solution is considered basic, or a base, when its pH is above 7. And what the scale measures and indicates is the number of hydrogen ions. These are cations, right? So we write hydrogen ions as H+, or hydroxide ions in solution. So an acid is going to have more hydrogen ions in solution, and a base would have more hydroxide ions in solution. At a pH of 7, the amount of hydrogen ions and hydroxide ions is equal. Anything below, a pH of a substance below 7 means that there are more hydrogen ions present. A pH of over 7 means that there are more hydroxide ions present. And let me give you an example of common household items that have a differing pH. So here's 7, here's neutral. So pure water, and we're talking not necessarily out of your tap, but like filtered water, should have a pH of about 7. Milk has a pH of about 7. If we move down the scale to more acidic substances, your gastric juice, the juice that's inside your stomach, has a pH of like 1.5. Let's see, orange juice is actually quite acidic, has a pH somewhere around 4. lemon juice, your sodas that you drink have a pretty low pH. Things with high pH would be, this is milk of magnesia, but you're probably more familiar with something like Pepto-Bismol, right? You take that when you have heartburn. Heartburn is where you have gastric fluid kind of regurgitating from your stomach to your esophagus. So you might drink some milk of magnesia, or you might take a Pepto-Bismol pill, and that is a substance that has a really high pH. And what that does is it kind of neutralizes that gastric fluid, so it doesn't cause you any pain, or it causes you less pain. Bleach is really basic. If you've ever cleaned with bleach or gotten bleach on your hands, you kind of feel that it's slippery, and that's an indication that a substance is very basic when it has that slippery feeling. So we often consider things that are acidic to be the worst, right? And they're the most damaging. But very strong bases can be quite corrosive or damaging as well. So if you've ever tried a hair remover on your body, or even oven cleaner, if you get oven cleaner on your skin or bleach on your skin, it causes damage to the skin, because high pH is very basic substances and very acidic substances. Both can cause damage. So safe things, at least as far as not causing harm to people, are right there in the middle. Okay, so what does all this mean, acids and bases, and how do we get those hydroxide ions and those the hydrogen ions and the hydroxide ions in solution? Anyways, so what can happen is water can separate. The hydrogen ion can pop off of a water molecule and leave just an oxygen and a hydrogen. So this is hydroxide. So when that water molecule comes apart, these are hydroxide ions, hydrogen ions, and you see how they're charged, right? Positive and negatively charged. So you have hydrogen ions and hydroxide ions. This is as a result of this water molecule breaking up for one reason or another and releasing hydrogen and hydroxide ions. And so this is determined by the substance that's mixed in water. So if you mix a substance that we call an acid with water, that acid releases hydrogen ions. So it releases more of these ions into solution. So that's why we call it an acid. It's an acid when it's mixed with water. So you get more hydrogen ions than hydroxide ions. A base accepts hydrogen ions in solution. So when you mix a base with water, it picks up those hydrogen ions. That base will hang on to those hydrogen ions, or those hydrogen ions will be pulled towards the basic molecule, and then what you have left free in solution are hydroxide ions. So that's just kind of a basic chemistry lesson for you. You probably all had this before. Here's a little graphic at the bottom showing you these acids where the hydrogen ions would be anchored to the acid molecule, but when you mix it with water, what happens is those acidic molecules, they free up those hydrogens, and now you've got free hydrogen ions in solution. And the same is true for a substance that is basic. You have the basic substance here, right? And when you mix that basic substance with water, it releases those hydroxide ions. So that's just a little picture of that. Not all substances release hydrogen and hydroxide ions when they're in water. Some compounds that dissolve easily in water release other ions other than hydrogen and hydroxide ions. So these things are called salts, and salts form when an acid interacts with a base. So here's a really good example of, this is called hydrochloric acid. It's pretty nasty stuff. It can have a really low pH. And this is sodium hydroxide. That's just the name of these two compounds. When you mix hydrochloric acid with sodium hydroxide, what happens is these molecules start to get rearranged. So look what happens. The sodium here comes away from the hydroxide and bonds with chlorine. So now you have sodium chloride. That's a salt. That's table salt, actually. And the same thing happens here. This hydrogen comes apart from the chlorine. And you know that the chlorine already bonded with the sodium, but where does that water go? That water bonds to this hydroxide group, so now you have water. We don't really deal too much with salts for the remainder of the semester. That's just something that we include here just under. So in living systems, when chemical reactions occur, when molecules come together, or when substances are dissolved in water, oftentimes hydroxide ions are released, or hydrogen ions are released, or hydroxide ions are released. So you would think in living systems, when these chemical reactions occur, you'd have these wild swings in pH, where maybe at during one chemical reaction you have a whole lot of hydrogen ions and not as many hydroxide ions, and then you have a lot of hydrogen ions, or let me rephrase that for you. And at another time you might have a lot of hydroxide ions and less hydrogen ion. And this is exactly what happens when chemical reactions occur. There's this fluctuation of the concentration between hydrogen ions and hydroxide ions because chemical reactions are constantly occurring in living systems. So this would be, if we had these wild swings like this all the time, then living organisms would have difficulty kind of maintaining a balance, kind of staying there right in the middle. So all living organisms have what we call buffer systems in them. And a buffer system is where we have some sort of molecule or substance dissolved in solution that is either going to donate ions or accept ions. So that if there are too many hydrogen ions in solution, a buffer might grab onto them. Or if there are too many hydroxide ions in solution, a buffer will grab onto them and pull some of those hydroxide ions out of solution, so that we get more of, over time, as chemical reactions occur in the cell, we don't get wild swings because those buffers are present to grab excess hydrogen ions so that the pH doesn't drop too far, and grab excess hydroxide ions so the pH doesn't go too high. Living organisms really rely on a steady pH, and we'll get more into this a little bit later as the semester goes on. But one example here is you've got natural systems in your body that should monitor the pH of your blood, for instance. And in most cases, in most individuals, your stomach acid is somewhere around 1.5, and the stomach is okay with that. That doesn't have to change. But when that stomach acid for some reason decreases in pH further and or starts to regurgitate up into the esophagus, that hurts, right? You feel that heartburn. That's literally the stomach acid kind of burning your esophagus. And so if this is stomach acid right here, one of the things you can do for, there's an arrow here, one of the things you can do for stomach acid is take something like Tums or Pepto-Bismol, and that's essentially what we call calcium carbonate, essentially chalk. So this has a high pH. Remember that pH was somewhere, somewhere up around 10. Right? So if you're feeling like you have heartburn, some of that stomach acid is regurgitating up into the esophagus, you take some Tums, and a few minutes later you start to feel a little bit better, because that calcium carbonate with a really high pH and the stomach acid with a really low pH right here, that calcium carbonate, that pepto, is going to disassociate some of those hydrochloric acid molecules and rearrange some of those atoms so that you have the hydrogen and the chloride that were bonded together in the acid that was causing you pain. That hydrochloric acid dissociates. It kind of breaks up, and then you have the calcium binding to the chlorine instead of the hydrogen, and you have the carbonate kind of disassociating here and creating a little bit of carbon dioxide. Anyways, my point is that buffers are present in natural systems to prevent wild swings in pH. Okay, so just kind of further explaining the importance of buffer systems. Buffers help maintain something called homeostasis. Homeostasis means same state. All living organisms, whether it's at the cellular level or tissue level, organ system level, like to maintain a steady state where most biological processes occur in a very narrow pH range. So the pH of your blood, for instance, has a very narrow range, somewhere between 7.2 and 7.3. If that pH goes down, that can cause severe issues, life-threatening issues, as well as if that pH goes up, that causes life-threatening issues. Most biological processes need to occur in a very narrow pH range, usually somewhere hovering right around neutrality. So if a pH of a solution changes, we call that, or a system, we call that acidosis. When the pH increases, we call that alkalosis. So let me give you an example. Every time you exhale, or let me go back just a second. Let's take water, or some water-based solution like your blood. When CO2 dissolves in water or builds up in water, you get as one of the byproducts this, which is called carbonic acid. It's an acid, so that's going to decrease the pH of your blood, right? So normally as you're breathing, you're dumping CO2. As you exhale, you release CO2 in the atmosphere. So you're constantly getting rid of that CO2. And your blood is a water-based solution. But let's say, for instance, you hold your breath and you don't get rid of this CO2, and that CO2 just begins accumulating in your blood, which is a watery solution, right? Accumulating. And after some period of time, you're going to feel an overwhelming urge to breathe. And that overwhelming urge to breathe is an indication that the pH of your blood is dropping. And your brain can detect that drop in pH of your blood. And so you consciously register this overwhelming urge to breathe, to exhale, to get rid of that CO2 and bring that pH back up to where it belongs. Okay? So that's just one example of how important buffer systems are. If you're going on to anatomy and physiology, you'll learn a lot more about buffer systems when you get into physiology. Okay, that's all I have. Stay tuned for the next lecture.